Hello friends, welcome back to Light Tutorials. In this video we'll see what is the MATLAB code for FFT, fast Fourier transform. Okay, if you find my videos in digital signal processing tutorials, the theory videos, okay, you can find these type of figures. Okay, but I hope all of you know what are these figures here. These are called butterfly diagrams, which we opt for solving a larger sequences in DFT by using FFT algorithms in a easier and simpler manner. Okay, so why we are going for FFT is it reduces the complexity of DFT from O of n square to O of n log to n. That means if suppose the number of samples are 8, that means for DFT it takes 64, let us say 66 of 64. Okay, whereas for this it takes only 3 into 8 24. That means only it takes 24 samples. Okay, and it grows slowly with larger n, works by decomposing larger DFT into several stages of DFT here. Okay, and also often provided as a highly optimized library. For these reasons we'll go with the FFT, not for, no, which is the latest version of DFT. Okay, updated version of DFT I can say. Okay, now this FFT in MATLAB, right? So in this example, I just considered a Gaussian pulse. Okay, this Gaussian pulse. Remember one thing: whenever you apply Fourier transform on Gaussian pulse, the output which you get is also a Gaussian pulse. Okay, whenever you apply a Fourier transform of on rectangular pulse, then the output you'll get is a sinc function. Okay, if you apply the Fourier transform of sinc function, you'll get sinc square. Okay, similarly if you apply the Fourier transform of triangular signal, you get sinc square. Okay, that means here I applied the Fourier transform on Gaussian pulse. Okay, now if you see, this is sampling frequency 60, and I have defined my time interval from minus zero point 0.5 to plus zero point 0.5 with a time gap of 1 by 60 seconds. Okay, here x is the my signal, 1 by square root 2 pi sigma is 0.01 here. Okay, 1 by square root 2 pi sigma is the Gaussian signal, into it's a constant into exponential e power minus theta minus t square by 2 into 0.01. Okay, now NFFT is the number of samples in the FFT here. That others is also called length of the FFT. It is 1024 samples. Now I have taken the FFT padding with zeros so that length of x is equal to NFFT. That means we don't know what is the length of x earlier, but here number of samples are 1024. For for the FFT is what? Correlation. I can say convolution, right? So for correct convolution correlation, the number of samples both x whatever say signal you want to convolve that, and the number of samples should be same, then only you get the exact output. So for that case I'm padding zeros with zeros. How many zeros I'm padding? I don't know the length of FFT, length of x, so number of samples which are there in my what in the length of the x, that many zeros I'm padding. Okay, I'm padding my x with the NFFT. Okay, after that I've taken the x, I've taken the thing into the x. FFT is symmetric, right? Because we have the similar sample. That means if suppose number of samples are 1024, we have 512 on the positive frequency side, we have 512 on the negative frequency side. Okay, I know arbitrarily there are no positive and negative frequencies, but for a matter of fact we'll write it on the mathematical graph. To plot it we'll do that. Okay, so it is a symmetric, right? So what I've done is here I've decreased my length from 1 to NFFT by 2. That means only 512. That means it is easy, right? If I calculate the response for one side, then I'll know the response for other side. That is easy for me. So I have decreased my length to half of it. That means 1 to 512 it will be. Now I'm considering the absolute value of capital X. That means I've got the magnitude. The spectrum plot is the same thing to magnitude and phase plot. So this evenly spaced frequency vector. Now f is from 0 to NFFT by 2 minus 1. That means 0 to n minus 1, n by 2 minus 1 into f is the sampling frequency by NFFT 1024. Okay, this is a vector here defining the spaced frequency vector. Okay, now I'm plotting it with respect, the figures are plot, two figures will be there. First one is figure 1, plot t comma x, this thing. I have plotted with respect to x. Why I am using plot? It is a continuous signal. Alright, minus 0.5 to plus 0.5. Next, I am plotting what? F comma mx. I am plotting my this vector frequency, evenly spaced frequency vector with respect to my magnitude. Okay, this is a Gaussian pulse signal. This is a power spectrum of Gaussian pulse signal. Okay, fast Fourier transform generally gives you the Fourier transform gives you the spectrum, right? So fast Fourier transform gives you the power spectrum here, right? Now run it. Now you can see this is my Gaussian pulse signal, and for this the power spectrum looks like this. Okay, now here you can see the amplitude is 4 here. The power is 60 dB, 60 watts, and that at up to 5 seconds. Okay, so this is how we perform the fast Fourier transform. Okay, here NFFT is the FFT is the function which I used here. Now if you can see here, you can search it in the search bar for FFT. Implements the transform and inverse transform pair given for the vector lengths. It returns the discrete Fourier transform of vector x computed with fast Fourier transform algorithm. Okay, what it discrete Fourier transform of vector x computed with a fast Fourier transform algorithm. We computed with the fast Fourier. Now FFT of x returns the fast Fourier transform each rows and column of the matrix. Okay. If I mention f of x comma, it is endpoint DFT. Okay. You can refer this in your MATLAB tool also. Okay. Sure. So this is it. Thank you for watching. If you like it, share it, and also subscribe to my channel for more videos. Thank you.